Thank you very much for your invitation. And I'm working in abstract augmentation, augmentation theory since quite a period of time, but I've been asked especially to talk about how we can use a SAT-based system for solving some of the relevant problem in augmentation theory. At the same time, I've been asked to give a small introduction on what is augmentation theory. I know that there are a few people in the room that probably just want to do your email instead of listen to me. That's absolutely fine. I will not take that personally. At the same time, I'm going to give a very skewed view of what is augmentation from my research interest. I know that other people are working in augmentation from a more human perspective, so try to support the way human are reasoning or in legal domain or in decision making. I'm just in this small context, in this small example, I will just look at an epistemic kind of reasoning use augmentation. So essentially try to assess what is true. And I'm just using this one as an introductory example that will lead me towards how we can actually use SAT-based system for solving some of the problems. So bear with me for the first 10-15 minutes. It's just going to be a talk, a chat about how can be augmentation, and then I'm going to go more in the nitty-gritty of the algorithm that we actually developed. So let's suppose that you start as any intelligent person with a question in mind, and you might want to research more about a specific topic. So you might want to have in mind a question like, does MMR vaccination cause autism? And you might go online and start collecting different sources of information and information from different sources. And then at some point you need to make sense of all the information you received. And as part of our project, we did when back I was still in Aberdeen a few years ago, and that was sponsored by the Ministry of Defense in the United Kingdom and the Army Research Laboratory in the United States. We look at how we can support the activity of sense-making using augmentation theory. And what I will not discuss today is how we actually transform language into knowledge, or whether there are different ways to represent the same knowledge into different formal knowledge bases. There are very big questions on how we can formalize adequately information and what are the criteria for logical formalization. I will not talk about that one. I will just give for the intuitive representation that we are going to give in terms of rule-based systems is reasonable enough for the work that we are doing. And in order to have humans involved, we are trying to not transform everything into pure mathematical logic, but we are trying to have something that takes the name of informal logic, and in particular argumentation schemes that are reasoning patterns that they are relatively easy for humans to understand, and they can be used as an intermediate way to represent in more formal terms something that you can just read or think. So this is how an augmentation scheme would look like. This is augmentation scheme from argument from correlation to cause. So it means that if your conclusion is that the A causes B, then you might want first to prove that A and B are correlated. And so this is the structure of an argument. But one of the additional power for critical reasoning that augmentation schemes provide are in the form of critical questions that are questions that you might want to ask in order to strengthen or weaken your argument. So you actually want to, for instance, to ask whether there is actually a correlation between A and B, how strong is this correlation, etc. And these augmentation schemes have been implemented in some sort of database structure since some years ago, and essentially we have all the infrastructure behind for handling this type of relationship and this type of information. So if we come back to our original question, does MMR vaccination cause autism? We can start from the hypothesis, the falsifiable hypothesis that actually MMR vaccination causes autism. And in order to do that, we need perhaps first to prove that there is a correlation between MMR vaccination and autism. So we look at the literature, and we might end up with this infamous paper from Wakefield and others from the late 90s. That was a preliminary investigation in the domain of MMR vaccination and autism. And the main claim of this paper is that one set of behavioral symptoms was associated by the parents with measles, mumps, and rubella MMR vaccination in 8 of the 12 children, and with measles infection in another child. So essentially, they took 12 children, and the parents of those children reported that there was an association between the vaccination and the insurgence of autistic symptoms. To be completely honest with true with the paper, the paper was a preliminary investigation. They claimed that it was a preliminary investigation, and they also had a long discussion when they said that they actually did not prove an association, but there is a potential for an association. So they did not claim that this is actually statistically significant. However, this paper is the main paper that has been cited by many of the people who suggest that vaccination causes autism, although it has been retracted. But let's take it. I will not discuss the sociological implication of this paper. So we can represent in the same diagram that we were having before, where these nodes now become rule of inference, and this box becomes information. In addition to this, our hypothesis here, we can have now that the association between MMR vaccination and autism can be supported by some witnesses, in particular the parents of these 12 children that report this correlation. And fine, you have a piece of evidence in support of it, but if you are following the Popperian view of scientific epistemology, you should not just look at what is supporting your claim, you should also look at what can contradict it. So you look again at the literature, you can find out this paper from 2002, and in this paper, essentially, they studied 537,000 children, and they did not find any statistical significance correlation between vaccination and autism. So, and actually, this paper was clearly, so they cited clearly the Wakefield paper, and they say this is actually to prove that this correlation doesn't exist. So if you can merge the information coming from the Wakefield paper here and the second paper on the bottom, and here there is a sort of conflict between them. And we can represent conflicts in argumentation in the sense that we can say that this element here, there is a correlation between MMR vaccination and autism, is contradicted by the fact that there is no statistical correlation, and we have 440,000 children. And so we can represent things in this format. It is a sort of glorified mind mapping, essentially. But the power of what we can do further is that we can start taking this graph and represent it in terms of rule-based logic. And I will just use one of the many approaches that are available here. I'm pretty sure that XU is a proponent for an alternative view. It doesn't really matter which one is not the topic of this talk. But you can essentially create a logic system here that has at least the concept of strict and defeasible inference rule. So you want to represent something in terms of rules, and you want to perhaps make a distinction between what is strict. So given the premises, the conclusion must always hold, and defeasible that even if the premises hold, maybe the conclusion might not hold because there are an exception or other elements. And you need a notion of contrariness. So you want to say that something is contradicting another piece of information. And in this approach, this notion is actually asymmetric. So you can have even that something is contradicting another object in your object language, but not vice versa. is just a matter of definition. Now, what we can do now is from this graph, each box can become now a proposition. That can be either true or false. There are extensions for handling degrees of true, so you can have probabilities. I'm not going to talk about that. And we can transform now each of those links into rules. So we now have that beta implies alpha, that gamma implies beta, that eta implies delta, and then that we have that delta is contradicting beta. So we transform whatever is written here that is fully understandable for humans into something that a machine can digest. And we appreciate that this is a very lossy type of translation. So we do not look at the meaning of each box. So I'm pretty sure that linguists in this room will be horrified by our approach. But once we have this knowledge base, then we can just borrow 20 years of research in this domain in order to build arguments and relationship between arguments. So an argument at this point becomes a concatenation of these rules in favor of specific conclusion. And you have the notion of sub-argument in the sense that you can have an intermediary conclusion before getting a bigger conclusion. So you have this notion of argument growing together. And you have the notion of attack. So if you have that a piece of information or a conclusion of an argument is negating the premise of another argument, then you have an undermining attack from one argument to another. If you have two arguments that have the same conclusion, one is the negation of the other, and they are clearly negating one each other, then you have what we call a rebuttal. Irrespectively of what is the definition of your conflict, you can now represent the entire information you have as a structure of arguments that represents inside all the chain of reasoning that brings you to a specific conclusion and conflict between those elements. So we can have, if we take this example here, we can have that there is an argument in the formalism we use. Each box becomes an argument itself, but this one then has gamma implies beta together with gamma gives you the conclusion beta, and gamma with gamma implies beta and with beta implies alpha is giving you another argument in favor of alpha. So you can create all those arguments, like this one is the one that I just discussed with you. And so you have here gamma alone, gamma implies beta, gamma implies gamma, gamma implies beta, beta implies alpha. And here you have eta implies delta, and epsilon implies delta. And because delta is contradicting with beta, then you have this unidirectional type of attack. So now we move from whatever was the representation of natural language text into sort of argumentation schemes, into rule-based systems. And now we abstract everything in terms of what are arguments. Each node in this graph is now an argument. And attacks. So each arrow in this graph is an attack, irrespectively of the way you actually construct those attacks. Now, this is this idea of this graph representing arguments and attacks is at the basic of abstract argumentation. So if you now forget about what is written inside this node, and if you just consider those nodes as the important bit, then you have what in 1993, it has been defined as an abstract argumentation framework. And in this framework, the atomic element is now not the logical language you are using to define your arguments, but the argument itself. The argument is the atomic element, and the attacks are the only important relationship between those arguments. And why this was defined? Because the idea was to define in some easy way what are semantics that you can have in order to identify what are acceptable arguments, acceptable set of arguments. So given a web of arguments and attacks, what you can say about it, what can be acceptable set of arguments that together survive the conflicts, that give you a coherent point of view. And this is the idea of argumentation semantics. So there are criteria to select set of arguments that satisfy some properties. And there are many properties. There are many properties that have been studied across the year. The original paper, I invite you to read it clearly, from Dung in 1995, is very interesting, and it comes from the logic programming view of non-monotonic reasoning. But after other researchers look at it in a different view, and I will choose this view because I think it's relatively easier to appreciate what is the ultimate goal of using Dung's argumentation framework. So you can have different criteria for selecting those arguments, and those criteria can how to say, obey some properties. So you can have, for instance, a property of conflict freeness. You don't want to accept an argument and the contradiction of this argument in the same extension, the same set of arguments that are collectively acceptable, and that is a relatively intuitive principle. You might also have the principle of admissibility, which means that you want the argument in this extension to defend themselves. So if an argument receives an attack, somebody in this extension, somebody in this set of arguments that are collectively acceptable must attack back, must fight fire with fire. You might want to have strong admissibility, so you don't want to say, well, if I have an argument A and argument B that are attacking each other, sure, I can accept either one or another. One can tell me tomorrow, now it's going to rain, the other one, no, now it's sunny. But you might want to have that your defense is grounded in something that is unattacked, that is uncontroversial, that is beyond doubt. And that is the idea of strong admissibility. Then you have the concept of reinstatement. This reinstatement means that if you have an argument attacked by another argument, and the second argument is in turn attacked by a third argument, so the third argument is reinstating the first one. So if you have A attacking B, B attacking C, A defends C, so A and C together should be acceptable, should make sense, right? I maximality, if you have a set of arguments that you want to consider, you don't want to consider anything that is bigger, that is containing, so you want to have maximality kind of constraint. You want to have the biggest with respect to set inclusion set. And directionality, you might want to consider that whether the status, whether an argument is inside an extension or not, depends only of the parents in the graph or not. And that is another possible property you want to see. Now, why those properties and why what we can do with those properties? We can start defining the semantics on this graph. And a possible semantics is the complete semantics that is satisfying essentially admissibility, reinstatement, and conflict freeness. And is telling that every is essentially a set of conflict-free arguments where each defended argument is also included. Which means that you can start looking at those four arguments here are unattacked. Therefore, they are, by definition, in this extension. Then we have perhaps that D here receives an attack from H, but is defended by this G. And so if we take D in this extension, it means that we can no longer take B. That's fine. And F as well, but F is already attacked by other arguments. So we can have, A, C, E, G as a possible extension. We can also add inside D. If we add D, we cannot add the B, but the alternative is we can take B and we don't take D. So is non-determinate, you can, each of those three options are complete extensions. Which one you are choosing is beyond the scope of the semantics. You might want to have the biggest one, but if you just take a complete extension, each of those it can be defined as a complete extension. Now there are other semantics. You can have the grounded extension, and at this point you start adding additional requirements on top of these complete extensions. You want to have the minimum one. So the minimum complete extension is going to be defined as the grounded extension is unique and is uncontroversial, yes. We don't have an empirical evaluation of which semantics make sense. So what, in concrete terms, what we are doing is instead we're showing to the user this one, which is the preferred extension. So they are the maximal complete extensions, so they are the biggest one, but clearly they can exist more than one. And at that point, we provide the user with two options. The first one is the skeptical acceptance of this one, which means that is the intersection, and that clearly is unique. But sometimes user wants to see what are the possible words that together make sense. So they would like to see, okay, either you accept this word view or you accept the other word view, but you cannot accept both together. So I appreciate that well, in the work that we generally do is we make the assumption that preferred extension are the one that we want to show to the user. Is not the only option we have. The reason for that one is it is one of the success stories, let's say, so of abstract argumentation. It is also the one that is satisfy more of the option of the properties I mentioned, and particularly maximality. It always exists. So it has a nice property mathematical, but we cannot guarantee it's the best one. But definitely, most of the people prefer to look at the skeptical part. So what is uncontroversial, what is in the intersection. That looks less debatable, let's say so. And as I said, preferred extension, essentially, you start from the complete, and you take the maximal one. Now, there is another one that is the stable. I'm mentioning just because it has a specific property. And the idea is you take the conflict-free that attacks all the other argument, which means that you want the stability here is defined in the way that you want to have something that is conflict-free and attacks all the other arguments outside. So there is no way you can get anything else inside. Now, this is defined in terms of extensions. I'm going to define the same concept very briefly in terms of what is called labeling, because that is going to be at the basis of the algorithm we are going to explore further. So instead of defining set of arguments as the acceptable set as the result of our reasoning process, we can define a labeling system of those arguments. So we can say that there is a function from arguments to a set of labels, and this set of labels is in, out, and undecided. And we just want to identify all those functions, and each function will have a one-to-one correspondence with a set of an extension that we defined before. And we have some constraints we want to enforce. So we want to say that this function can label an argument as in, if and only if all the attackers of this argument are labeled as out. An argument must be labeled out if there is an argument is attacking it and is labeled in. And if these conditions cannot be satisfied, then the argument is undecided. So this is the definition of this function, and which means that, for instance, all the unattacked arguments by definition are labeled in, always. Now, if we label this argument in, this argument must be labeled out, because there is at least one attacker that is labeled in. So this argument must be labeled out. Now, at this point, let's take this D and B. We can take can we label out? No, we cannot label out because there is no attacker that is labeled in. Can we label in? Well, yes, we can. If we can label D in, then we need to label B out. But at the same time, we can label them as undecided because it's absolutely fine. So if we label them as undecided, this comes down to be exactly the shortest, the smallest complete extension we saw before. If we start taking D inside and then this become out, then we have this complete extension, and vice versa, we have these other ones. So essentially, it has been proven that the labeling with those conditions provide the complete extensions and vice versa. So you can go from one other to another. And if you want to have if you enforce that you don't want undecided, then you have the stable extension, because it means that no argument can be undecided. Either an argument is in or out, because all the arguments must be attacked by your extension otherwise. And the preferred semantics is the maximum in argument, essentially. Now, as I was mentioning, preferred has very nice property apart from strong admissibility. So the only one that satisfies strong admissibility is the grounded. But the grounded has sometimes the problem that if you have cycles, might just end up to be empty. So that's why the second best choice seems to be the preferred. The stable has the strange property that doesn't satisfy directionality. Also because stable is, among those 4 semantics, is the only one that can even not exist. So you cannot, the simplest case is having an argument that is self-attacking. That is impossible to have a stable extension. So given these results, you can even, if you remember our example before, you can compute at this point a semantic extension on top of this. And in this case, all the semantics will just come back with the same results because there are no cycles in the graph. And you have that these 3 arguments are labeled in, those arguments are labeled out, and you can just go back in what we did before and having the conclusion of the arguments that are labeled out, these 2, as crossed over. So you can say to the user, well, you should reject your hypothesis, because although there are some piece of evidence in support of this claim, there are stronger evidence against, essentially. Now, and this comes the part that I've been asked to cover mostly in this talk. So how we compute semantics extensions. Now, we know that for those 4 semantics, we already know that have already been studied since quite time the computational complexity of different problems. So we distinguish the problem of existence of at least one semantics extension, and that is trivial for all the semantics apart from stable that is NP complete, because stable might not exist, and you essentially need to find at least one extension to prove that it exists or not. Credulous acceptance, it means that given an argument, identify whether this argument belongs to at least one semantics extension or not. And that is NP complete for complete, polynomial for grounded. Grounded is always polynomial. Preferred is NP complete, and stable is NP complete as well. Skeptical acceptance, you want to check whether an argument belongs to every single semantics extension. And that is polynomial for complete, but is at the second level of polynomial hierarchy for preferred. And verification, given a set of arguments, verify whether that one is an extension. And the last one is non-emptiness, is whether you want to identify whether there is at least one semantics extension that is not empty. So there is at least one argument that is accepted. Now, for reasons that I mentioned briefly before, we focus on preferred semantics. And preferred semantics is, by a long time, the hardest among those four semantics. So there were several attempts in trying to do reasoning with these semantics. And a few years ago, independently, the group in which I was working at the time and a group in Vienna came out with the idea of using such solver as an oracle for reducing the complexity of this algorithm. Now, Vienna published a few months before us, so technically they came first, but they use a slightly different approach than what I'm going to say. So essentially they use a SAT-based system, but in a slightly different way. However, last year, the system that I designed won the first place in the preferred semantics track of the international competition in computational argumentation. So that is the reason why I'm presenting you this approach. In honor of truth, this competition was organized by Vienna, so Vienna could not participate in it. But that is something that I will omit from this recording. To be fair, in the previous edition, we came first regardless than Vienna. So it's an interesting competition between us and them. So this is based on a paper that we published some years ago, and I will mention also some additional interesting avenues that we took after. But the essence is relatively simple and relatively based on this paper here. So let's think about, again, the labeling constraints. So we have a total function. We know that if an argument is not attacked, then must be labeled as in. And then we know that if an argument is labeled in, if and only if all its attacker must be labeled out. So there is a if and only if condition. Then we have that an argument is labeled out if and only if there is at least one attacker that is labeled in. And then the last condition, you can rewrite it as an argument is labeled out if all its attacker are not labeled in, and there is at least one of its attacker that is labeled undecided. Then that is the only condition that is giving you as an undecided. Now, you can transform these conditions into a SAT problem by providing for each argument 3 different variables. One for this argument is labeled in, one this argument is labeled out, and one is labeled, this argument is labeled undecided. So this one should be laid. Given an argument between 1 and k, I means this argument I is labeled in, or this argument must be labeled out, or must be labeled undecided, but you cannot label at the same time either in and out, so it can be only one of them. So this first line says that you must label either in, out, or undecided, but you cannot have more than one label at the same time. And then you can start, so this one says that if you don't have any attacker, then this must be labeled in, and not labeled out, and not labeled undecided. Otherwise, you enter a big, if you have at least an attacker, then you can transform the first condition. So labeled argument A1 is in, if and only if this one. So you can bring this one into 2 material implication. One from left to right implies right, and the second right implies left. And you can transform this material implication into a disjunction. So once you have this disjunction, you can just represent it in SAT formula. So you can just represent this one says if the argument is in, or all its attacker are not out. And that you can go on and represent all the material implication in this way. And so this is the complete, the total, the SAT representation for the problem of computing complete extensions, or solving, identifying what are labeling functions on your argumentation framework. Yes, it is because we know that there is always a complete extension. It might be that it comes out to say that there is no in argument, but it is always satisfiable. Now, a small point that is quite important from a practical point of view. Now, these set of definitions are redundant. Well, these conditions are redundant because we already know that a lab is a total function, which means we know that if it is not in or out, then it must be undecided. Which means that if we enforce that this is a total function, then we don't need, for instance, the last line. Just the first 2 lines just suffice. So if we can just remove some of those SAT formula from before sending to the SAT solver. Equivalently, we can remove each of the other line independently. So we can remove the first line or the second line. But also we can keep the total function and just have the material implication from left to right, or from right to left. And some of those equivalents were already proven before. In that paper, we also proved that all the others are trivially equivalent. But why this is important will come over in a second. Now, let me explore with you what is the actual algorithm we derived for computing preferred extensions. Because so far, I just told you, given a complete extension, given a labeling, we can just transform into a SAT solver. But now we know that we have to identify the maximum of those labelings, the labelings that maximize the in arguments. So essentially, we just do a sort of hill climbing, try to get more arguments inside of our complete extension. It's not particularly complex. The pseudocode is boring. Let's go with an example. So this is an argumentation framework where you have this cycle here, F attacks E and vice versa. A attacks A and B attacks each other, B attacks C, C and D attacks each other. And we know that those are the complete extensions. I just give it to you. It's fine. Now, what the algorithm does is it starts from a complete extension. So essentially, we take the search formula, the CNF formula that I showed you before. We send it to a search solver. It comes back with an assignment of these labels, and we just take those labels. So perhaps it starts saying, OK, F and D are in, E and C are out, and A and B are undecided. And this is a complete extension, and that's fine. What we do next is we force the search process to find an additional in argument that are outside the complete that we found, which means that we now ask the search solver, OK, give me another complete where F is in, D is in, and at least either E or A or B or C are in. So we just add this additional clause when we are forcing this to be in, this to be in, and then we have a chain of or that say at least this one or this one or this one or this one must be in. And then the search solver comes out with another solution, if there exists. Fine, we found this one now. And then we can just ask, again, the same thing to the search solver. So we identify what is not in the preferred extension. E, B, and C are not in the preferred extension. We can ask again, can you give another complete extension that has those one also inside? And at that point, it comes out to unsatisfiable, because there is no way you can satisfy it, which means that the previous one we found is the complete extension. And then we go on and we say, OK, we now saved what is the preferred extension we computed before. We know what is it. We now need to force the search solver not to get back to that solution. So we add some blocking clause in the search, and the search solver comes out with a different solution, and we repeat the process until we can no longer find a satisfiable solution. Now, we did an empirical evaluation of this approach. I will not go into the details of, let's say, competitors. I will invite everybody to read the report of the International Competition of Augmentation. So we considered different search solver. At that time, we used Precosat, that was the winner of the SAT competition in 2009, and Glucose in 2011. We now have also Minisat as a library. Unsurprisingly, Minisat as a library works better than everything else you want to use as a pipe command on an operating system. We randomly generated different argumentation frameworks with the set of arguments ranging from 25 to 200. And we also variate the probability of attack. So essentially, we had an Erdős-Rényi type of graphs behind. The competition used also a different random generation system. We also tested other system as well. Performance vary clearly on the structure of the graph, and therefore all the results needs to be taken with a pinch of salt, of course. But the measurement that we used was borrowed from the International Competition on Planning. And that says, OK, for each argumentation frame, for each problem, you take the best execution time among the competitors. And then you consider all the other competitors with this formula. So you take, if this is the second best, you take this time over a logarithm, and that is at the denominator. And you keep adding all those scores. So essentially, the highest score is the best one, and then all the others just comes down with a logarithm, so you don't have big bump, essentially. The first thing that we started is, although the different encodings I show you are logically equivalent, whether they make a difference from a computational perspective, and they do. They heavily do. So those are just given our system, no other competitors, but we just run with different encodings. And this encoding here, that is, when you just have the material implication for all the three conditions from left to right, sounds to be consistently the best one. And the reason for this one is now under submission to IAJ, so I will not tell you. And you have to wait for the reviewers to know it. But essentially, it exploits very nicely the way the search solver works. But the others, although they are equivalent, they have a significant drop after when you have argumentation frameworks bigger than 100 arguments, essentially. And if we compare our system with state of the art, then the system work very nicely. So these two lines that are overlapping with triangles and circles here are our system in the case of whether they're using Precosat as solver or glucose. And all the other two lines instead were the competitors that we considered. They were the best one. One was using answer set programming as a reduction-based system. So they were reducing the problem of computing preferred extension into an answer set program. And Nofar, Dunn, and Atkinson instead propose a search algorithm within the labeling system. So they actually develop their own search algorithm instead of reducing the problem into a SAT or to an answer set program. And so good, right? But, well, same stuff. But then we start thinking, well, true, but is there anything we can actually explore further from the structure? Because right now is a relatively brute force type of approach. You just start from an argumentation framework, you just transform into a SAT problem, you just ask the SAT to do all the work for you, and then you just sit back, relax, and do the small step to improve it. But there are some elements that we know that we can exploit from the theory of abstract argumentation that we can use for improve our algorithm. So for instance, if we take this graph here, it doesn't matter the meaning of those nodes. What we can start doing is identifying the strong connected components, because we know from a very nice set of theorem that my PhD supervisor wrote, that if we want to compute the preferred extensions, we can explore the SSE structure of a graph and start computing preferred extension only on this subgraph, and then propagate the results over the other subgraph of the other components of your SSEs. So essentially, you have this nice property, which is, by the way, works with some but not all the semantics. So for instance, stable, because it doesn't satisfy directionality, is going to be much harder to make it work in this case. But preferred supports satisfies directionality, so you can just apply in this case. So this is what we did. We essentially created these, we identified those SSEs, we ordered them. At this point, we know that SSEs can be easily ordered, because if you just collapse an SSE as a node, then you have a directed graph. And we start computing preferred extensions here, and then for each preferred extension we compute that, we can propagate further, right? So if this one is an attack, therefore is always in. And if this is in, then we know that B cannot be accepted, these SSEs just disappear, and now this one disappeared. But at this point, here we broke the SSE. And the approach that we use is called SSE Recursiveness, because at this point, this SSE, you can reapply the same approach, and you can redecompose what you broke before into two different SSEs and reapply recursively the same scheme. And it has been theoretically proven to be equivalent, which means that essentially we can reduce the problem we are going to ask the SAT solver in smaller and smaller bits. More frequent, but smaller. So how we can explore SSE recursiveness in an algorithm and whether it's worth doing it. And this is another boring pseudocode, but let me walk step by step essentially. We first do the grounded extension, because we know by theoretical studies, we know that the ground extension is going to be always inside every preferred extension, so this is just a pre-processing stage, not very interesting. Which means that in this case, in the example, the grounded, we just say this is in, all these three are out, and this is in, and for all, and this is out. And everything else is just undecided, and this is the minimum complete that you can compute. Then we essentially look at the rest of the graph. So we ignore everything before, and we identify the SSEs in this graph, and we arbitrarily start from one of them, And at this point, we can no longer decompose any further, right? So now we have to do the hard job. But at this point, we can reuse essentially the same algorithm we had before and essentially compute the preferred extensions on this subgraph in the exactly same way that I showed you before. And once we have these preferred extensions, then we need to go back and see how those different preferred extensions propagate on the rest of the other SSEs. And now the experiments we run was showing whether once we have a single SSE, and we assume that this decomposition system would perform worse. That was our hypothesis, because we have to do this pre-processing, and that is probably ineffective. If there is we also check whether there is a value that is telling us after a certain amount of SSEs in the graph, then this decomposition is actually going to give you some performance advantage. And then the idea is when we are getting very big graphs with a lot of SSEs, that you can have a significant difference between the performance. So this is the graph with a single SSE, and this is the approach I showed you before, and that performs significantly better than all our improved algorithm, because our data structures are not particularly refined, definitely not refined as the one of the SAT competition, and we are trying to do something clever that is unnecessary in this case, because there's just one SSE essentially. But if we have more SSEs, then there is a point where these two lines cross. So there is a point when we have at least 35 SSEs using these benchmarks, where using the decomposition is actually giving you an advantage. And if you start having the number of preferred extensions here, actually having the decomposition is going to give you an advantage. So if you know that you're going to have enough SSEs and enough preferred extensions, then doing the decomposition is giving you an advantage. If not, just use the traditional algorithm. And the next step clearly was, at this point, well, we can parallelize. Because after we start cleaning the SSEs, if we arbitrarily need to start from one SSE or another, and those SSEs are no interaction between them, or we already started interaction before, we can continue doing this kind of stuff in parallel. And in this paper submitted we published in AAAI, we actually proved that there are significant advantages in doing that if you have enough parallel processing and if you have enough SSEs, of course. Now, I will not go into the detail of that version, because it's just a parallel version of what I just showed you. And I will just sum up for the talk of today. And we focus very much on preferred semantics. There are many other semantics among also not just the 4 that I showed you before, that were the original 4 that has been provided by Jung in 1995, but we have a zoo of semantics. And now we also enter the idea of having graded semantics, so where you don't have just in, out, and decided, but you want also to have numbers associated to how much you should believe that an argument should be in this extension or not. And this is an entire other chapter, if you want. SAT-based reduction seems to be rather efficient, no less because we won the competitions, both of them. But at least for some of the problem in the first one. And if you want to do something really clever, then you are paying the price of over-engineering or doing the decomposition steps, unless you're doing very efficient data structure and you're doing your algorithm very optimized, especially because now such solver are very, very sophisticated piece of machines. What we also did, and I did not talk about, is you published a paper in HR where we talk about we rerun the competition of the 2015, and we analyze further what are the relationship between the structure of the graph and the performance in order using essentially standard machine learning and greedy algorithm to identify what are the features of the graph that are more important for performance. And it turns out that it's not always true that stat-based systems are the best. So there are structured graphs with specific structure where approaches that are not translating into stat, but just try to do the search in the original graph are much more efficient. And there are other graphs for which instead moving into an answer set program is much more efficient. So as always, the results of a competition must be taken with a pinch of salt. We also published a paper in which we use machine learning for predict some structure. So instead of actually computing preferred extensions, seeing whether we can predict at least, I don't know, the number of preferred extensions or whether at least a preferred extension exists or not. And we had some interesting results. But this is an entire open field of research. And if you are interested in general on this topic, this is clearly a very short introduction and very biased. Also, no last because I presented only my system, well, the system that I developed with many colleagues. But we published in the Journal of and their applications, but a chapter that is also included in the first volume of the Handbook of Formal Argumentation. So that is published by Dovka Bay College publication publisher. And this chapter lists all the current implementation, describes the structure, how they work. We do not go into the direction of proving the efficiency because there is the competition now, and there is an artificial intelligence journal paper of the first competition with all the nice results, and is coming also a paper for the second competition. So with this one, I thank you for your attention and your patience, and I welcome questions. Thank you very much.